symmetry, which we call S sub P, symmetry, which fixes the point and its derivative at that point is minus identity. And the consequence of that were that M is complete plus homogeneous, and that it flips to S6. So X per P of T times V. That suggests. So this is, by the way, often my notation. I also call that gamma V sub T. Okay. So the initial direction is V, and I put it at the foot point here for shorthand sometimes. So this is taken to under the symmetry at P to X per P of minus TB. So gamma V of minus T. So it flips to S6. Let me make one more comment about the example that I discussed last time. We said the Grassmannian is symmetric. This embedded into a vector space, which was the set of all n by n matrices, with the property that they are symmetric. And okay, that was symmetric. I think that's what was our setup, and the inner product was a trace of the product. And then we showed actually, so that if I take I can formulate like this now. If I take say P contained in Rn is a K-plane, or maybe P comma Q, so let's take two K-planes, then the symmetry around P of the K-plane Q is simply the reflection in E around Q. Right, where the reflection preserves E and is minus identity on E perp, the usual reflection. So for each vector, just send it into that reflected vector. That gives you another plane, and that's a symmetry. So we showed that's an isometry. It's a symmetry in the sense, so it's a symmetric space. So one more comment. First, as we discussed, this actually sits inside the subspace W, which is those P and V, where trace P is equal to K. It is guaranteed that the planes are K-dimensional. So actually in this space V here, I have all the Grassmannians sit in there in different affine subspaces. A collection of all the Grassmannians are subspace in this here. And one more comment is that if I look at the inner product, so if P lies in here, so how would you define the Grassmannian? Grassmannian here were defined as projections, such all P and V, such that P squared is equal to P. And the image of P was on a K-plane. So that was our definition. So they sit in there at different levels, and so if I take a projection in here in this sense, what is its length? Squared, so it's inner order of P comma P. Well, that's supposed to be the trace of P squared. But P squared is P, and the trace of P is K. Right, so they all sit inside a sphere. K is fixed. So in this affine plane here, there's a sphere of a certain radius that depends on the particular value of K I choose, and it sits in that as a sphere. So actually, it's a codimension 2 submanifold inside V here, in that sphere. So usually one considers a Grassmannian as a submanifold of this sphere here. It's kind of nice. So I mentioned, for example, the lowest dimension one, RP2 in this fashion sits inside S4. That's a famous embedding. Okay. So that much about elementary properties. And now one of the tricks that one uses to study symmetric spaces is that one defines what are called transvections. So for this, I choose a geodesic gamma of t. And I look at the reflection, the symmetry around gamma of t over 2, and which way around I want to do it, before or after. Before. Composed with a symmetry around gamma 0. So call that t sub t. So these are isometries. Composition of isometries. These are called transvections. So let's prove some properties of these transvections, which are going to explain the name and consequences. So let's see, what do I want to do that? First, what does it do along the geodesic? It just translates the geodesic by adding the value of t, this transvection, to the parameter. The derivative of this transvection at the point gamma of t, gamma of s, is paratranslation along gamma from, well, it's from gamma of s to gamma of s plus t. So part A says that's from where it goes. So it's just given by paratranslation. And let's see. Yes. It's one parameter group of isometries. So it's called a one parameter group. In fact, if you want, it's in a Lie group, right? We said that the set of isometries is a Lie group for a given manifold M, I of M. That was my notation for the isometry group. So inside that Lie group, I have these kind of one parameter groups. Okay, so if I have a geodesic gamma here, so these transvections take gamma of s to gamma of s plus t, and along there it's paratranslation in this sense. It's a very special property. So let's prove these things. So I have to reflect two reflections, one around gamma 0 and one around gamma t over 2. Let's first think about what does a symmetry around gamma of t do to gamma of s. So I claim that's gamma of 2 t plus s. Minus s plus s, I keep forgetting. Minus s. So let's draw a picture. Here is gamma of t. Here is gamma of s. So distance from here to here with t minus s. I reflect, so this distance is also t minus s. Right, I just reflect along the geodesic for the symmetry, that's what we said. So this here would be gamma of t plus this 2t minus s. Okay, so that's what it says here. Right, so that's how it translates. So if I look at this composition now, s gamma of t over 2 composed with s gamma of 0, and apply this to gamma of s, I get s gamma of t over 2. S gamma 0 would be a gamma of minus s. Just reflect around 0 if you want to. And this is now s of, is going to this here, gamma of 2t, that's t, minus s. It's minus s, which is plus s. So indeed, it takes gamma of s to gamma of t plus s. Just translates along the geodesic. That's one reason why they call transvections. Things that translate along the geodesic, like this, are called transvections. That's part A. Part B is then a consequence of that these things are isometries. So remember, say, if f is an isometry, f takes geodesics to geodesics. Say gamma to f of gamma, right? And parallel vector fields along gamma to parallel vector fields along the image. Right, the isometry preserves the metric, preserves the connection, preserves the curvature. Preserves the connection means it takes a geodesic to geodesic, and parallel vector field is number x equal to 0, so it takes parallel vector fields. So what does what's TT do? Well, first, let's say what does it's a composition of two things. Both of these are isometries here. So I can say that S a gamma of, so let's do a general T for the moment. So let's say X is parallel along gamma. Then I take the image under this isometry of the vector field X along gamma. That's again parallel. Along the image geodesic, but what's the image geodesic is just gamma itself, just reversed, right? Along gamma of minus t, if you want to. And what are the initial conditions? So the derivative of, say, S gamma of t at gamma of t applied to x is minus x, by definition of the symmetry. Right? So it's a parallel vector field along this parallel vector along the geodesic, applies symmetry, it flips the geodesic, takes a parallel vector field again to something parallel, but at the base point it just takes it to minus x. So what does that say? That simply says that the image, so S gamma of t star x is equal to minus x. Parallel vector field is determined by the value of one point. So look at this point. This takes x to minus x. That's true at this point, so it's true everywhere. So these two parallel vector fields agree. Up to a sign, up to a sign. So now I have to do it twice. Right? So now I take t star of x. Well, it flips it twice, right? This here flips it at the point gamma 0, changes the sign. This flips it at the point t over 2, changes the sign again. So it's just simply equal to x again. So indeed, the image is of a parallel vector is again parallel. And that's what this is right here. Right? What is this here? This is simply the derivative of t along the point gamma s applied to x along the point gamma s. Right, so that's what it is. So, and this is, it's just x itself again. X was parallel. So I can just think of that. That's exactly what the derivative does. Right? If I want to understand the derivative along gamma of s, it takes gamma of s to gamma of s plus t. I want to see what does it do to a vector v that's tangent at this point. So what do I say? Well, I say take the unique parallel vector field, which has a value v at x. And then this is again a parallel vector field. The image is a parallel vector field. So that means the image vector simply take that vector, parallel translate along it. Okay. So indeed, the derivative is just another way of looking at parallel translation. It's kind of built into the symmetries. Right? the symmetries determine pair translation. It's kind of interesting. They're more powerful than you think, these symmetries. They have all kinds of nice consequences. Part C is then follows from that easily. So let's look at the pair translation by S plus T, the transvection by S plus T, and the transvection by S composed with the transvection by T. These are two isometries. And we already discussed last time isometries are determined by the value at a point and by the derivative at a point. So where does it take, for example, gamma at 0? It takes the gamma of S plus T. Here it takes this gamma of 0. First add T to 0, and then add S to T. That's the same point. And derivative of Ts plus T at gamma of 0 is pair translation. And Ts composed with derivative of Tt, here I guess gamma of 0, gamma of T, is a composition of pair translation. First pair transfer from 0 to T, then from T to S. It's the same thing as going from 0 to T plus S. The hints are the same. Which implies a claim. They agree at the point when derivative agrees at that point. So they're one-parameter groups. Symmetries themselves are not, but a clever composition of symmetries is a one-parameter group. And especially part B here has powerful consequences that these derivatives of pair translation. So for that, let me discuss a little bit what one can do with pair translation. One can define what's called the holonomic group. Of a Riemannian metric, it's even defined for a connection, but we're going to do it for the Riemannian metric. So what is that? I fix a point in the manifold. Let's say gamma be closed, say piecewise smooth path, where gamma of 0 is equal to a point P, and that's gamma of 1 also. And now look at the group, which I call hol P, which is a set of all P gamma, where gamma is a closed path like that. And P sub gamma is pair translation. Along the path gamma. So take any closed path, pair transit around it, and I come back with a different vector. And I got a linear map from here to here, from here to here, which is this vector to this vector. So this becomes a subgroup of the orthogonal group of the tangent split at the point M. For a metric, right, pair translation preserves the length of vectors, so it's an isometry. I always come back to the same point, so I just get an isometry of the beginning point. Okay. A pair translation is linear, right? So it's really a linear map. Okay. So that's called the holonomic group at the point P. And now I can prove the following things. About this group. And some of these are not elementary. First, what is true is what you would hope to be true, that this is a Lie group, like the Lie subgroup of this Lie group. You certainly expect that to be true. That's part A. Of the orthogonal group. That's not elementary at all. It's not a closed subgroup in general. Part B says that the identity component, which I'm going to call ball 0p, is compact. Part C is this identity component can also be looked at in a different way. It's parallel translation along closed path where gamma is null homotopy. And this then becomes a subgroup or the special orthogonal group of TPM. But one direction is obvious. If I take a path that's not homotopic, I get a curve of pair translations. So certainly this should be contained in the identity component of the full polynomial group. So inclusion from here to here is clear. The converse isn't clear at all. Take a pair translation. It's pair translation of some path. I forget about what path I care about. I only care about the element in the polynomial group. That's just an orthogonal map there in tangent space. If I have a path of such maps to the identity, I must construct a path of closed curves with a null homotopy where that's a pair translation. That's not clear at all. Like, that's not how you prove it. But that's certainly important property. What else? Maybe all P is independent of P in the following sense. So at least as a Lie group, it's independent of the point. So let's take a point P, let's take a point Q. I can define hol P. I can define hol Q. Of course, they act on different vector spaces now, so it doesn't really make sense they're the same. But how would I compare them? Well, I would take some path, fix a path, gamma naught from P to Q. And now I can compare the two. So I could first take some closed loop here. So which way around do I want to do that? Or should I take an inverse? I want to go from, I want this to be hol Q. From Q to Q, I first take gamma, then I take the closed path, and I take gamma inverse. Right. So that's a natural comparison, and they're the same in that sense. Particularly, they're isomorphic as Lie groups. Not in a natural way, because this isomorphism will change if I choose a different path. I get a different isomorphism. So not natural in a sense, but as Lie groups, they're the same. So I might as well talk about the holonomic group and not worry about the base point. Maybe another property is that if M is flat, then hol P0 is just the identity. On a flat manifold, the holonomic group, at least the identity component, is trivial. Full group may not be, so it means hol P is a discrete Lie group. But there could be non-trivial elements in it. For example, if I look at the Möbius band, it's flat metric. Then take a closed path that goes from, say, from this point to this point, which is equivalent. That's a closed path in the Möbius band, and then what does power translation do? It takes this vector to this vector, but that's the opposite vector identification. So for this path P gamma here, this path gamma, P gamma, is my identity. Okay. So whole P in general is discrete. What's surprising, and this was a long-standing open conjecture, well, since this identity component is compact, probably the whole normal group should be compact, the whole group, whole P, and that's not true. So there are examples where P is not compact. In other words, there's infinite many components. Of course, notice that this combination of this and this implies that if M is simply connected, then it is compact. Because then whole P is just the identical component of the group, and part B says it's compact. So one consequence of this is that if pi1 of M is 0, this implies that the whole number, the full number group is its identity component and is compact. So that's something important we're going to use sometimes. What else? Well, maybe one other fact. What about the Lie algebra of the holonomic group? Right. So, is there a question?
You said there that you have examples. The holonomic group is not compact. But where are those examples?
Oh, I didn't give you one.
Oh, okay.
They're non-trivial. Was a conjecture for about 30 or 40 years that the group is compact. And in fact, the counterexamples were given in Burkhard-Wilking's thesis. That was his thesis, his PhD thesis. They are left in varimetrics on certain solvable Lie groups, where he proves that this group has infinitely many components. They're non-trivial. Well, maybe one, so maybe CD. If M is compact, then whole P is compact. So it is true for compact manifolds that whole P has finitely many components. Right? But if it's true if it's simply connected, it's true. If it's compact, it's true. But in general, it's not true. So here there are examples of left-invariant metrics and solvable Lie groups. Let's do two more couple. Okay. One more fact. So what about the holonomic group of this Lie group? Yes? Yes. Let's see, what can I... Yes, indeed, that is indeed easy because there's a nice homomorphism. So I can go from pi1 of n into whole P divided by whole P0. So this here is the anti-component, so it's a normal subgroup here. I take a quotient. It's like the group of components, if you want to. The question is, how big is this finite group, this discrete group? And I claim this is onto, where I just take a homotopy class of something in gamma into our translation around gamma inside whole P. So it's a tautological map. Right? And what's the kernel? Well, it's non-homotopic. It lies in here. So therefore, I get an induced map like this. clearly everything by definition lies in the image. So I get a homomorphism. So F is a homomorphism, which is onto. So it gives you a bound on the number of components. Right? You can have only as many components as per 1 has at most. Okay. So if per 1 is finite, there are only finite many components in particular. And so in these examples, in fact, you have to take the Lie group, such a Lie group, and divide by some group gamma in order to make pi 1 infinite. So it's a quotient of a solved Lie group in these examples here. The counterexample must have pi 1 infinite. One more property. So some things in the Lie algebra are easy to describe. First, Hall P sits inside a Thorgan group, so Lie algebra must consist of skew-symmetric matrices. So let's look at the Lie algebra. It contains certain elements, namely, let's look at the curvature tensor. So at the point P, applied to two vectors v and w. Which takes a z into the curvature applied to that. The claim is that for any v and w, this endomorphism RVW is an element in the Holonomic group, the Lie algebra Holonomic group. So curvature endomorphisms is something in the Lie algebra. So in a way, the holonomic is very closely connected to the curvature. In fact, there's an exercise in Ducamo which says that. I don't know if you've done this exercise. It goes as follows. It's a very nice exercise, but I actually like it. So take a point P, take my two vectors v and w at this point, and construct a two-parameter curve. So for minus epsilon, epsilon across minus epsilon, epsilon into m, such that it starts at P. In fact, for any starts at P, and gamma S is equal to V, and gamma T is equal to W. So construct a net, if you want to, right, which at the beginning point has as a two coordinate vectors of the net V and W. You can clearly do that, right? The exponential map or something like this, because I only require this at the point. And now to do the following. Let me draw it schematically in the picture over there. I can define a map Ps, T per translation by going T in this direction, S in this direction, and then back. That's a closed path which starts with this point P for each S and T. Let this be pair translation along this closed path. And then you show that the derivative d ds, d dt at s equals t equals 0 is equal to r vw applied to x. So in the sense, if I apply this to x, other way around. Sorry. Okay. So go around the closed path. I get a pair translation. So I get a curve in the tangent space there. They all have symmetries. So it's a curve in the orthogon group. I now differentiate in both directions. What you get is just a curvature tensor. So for me, this is in fact the most geometric way of visualizing the curvature. It's the deviation of pair translation to be independent of the path. That's kind of what it is, right? If it wouldn't depend on the path at all, then I would always come back to the identity. Because I can go there. For each t and s, I would get the same thing if it's independent of the path. So then this curve with identity derivative would be 0. Right? So this curvature matters deviation of pair translation to be independent of the path. That's an exercise in Tucamo somewhere. I like that exercise. So that explains this property right here. You can do a little bit more. So this is not the whole Lie algebra. There are other kind of curvature endomorphs in there also. And one can actually describe the whole Lie algebra in terms of curvature, but I won't do that. Well, maybe I can say the following at least. It's a theorem, but it's actually not that useful. An interesting theorem that describes the whole Lie algebra. Let's do it to Ambrose and Singer. Which says that Hall P is spanned by things of that form and cone derivatives. So higher and higher order. So take the curvature endomorphism, differentiate the curvature. I get another tensor, apply that to V and W, it's symmetry again, get more and more terms like this, and this eventually get the whole Lie algebra, the whole number algebra. So it's just curvature plus their derivatives. Okay. So just some overview of things about the whole number group. I don't need that much in the rest of the course, but it's kind of interesting what one knows about the holonomic group. Maybe some more philosophical comment about this. Which is similar to things that we said before. So we have our holonomic group, and it acts on TPM. It's a representation of the tangent space if you want to. Right? One can try to examine this representation. If there exists a tensor, it's called T, on TPM, such that T is invariant under the action of the holonomy, then there exists a tensor, let's call it T bar, on M, such that T bar at the point is T, but so I can extend it, and T bar is parallel. Whatever sense your parallel is supposed to mean. So this is kind of important principle in many different contexts. Right? So I have my tensor at the point P. Think of a vector, think of an endomorphism, think of a curvature tensor, any tensor you want. Right? Think of a complex structure. Something at one point defined, undefined everywhere else. So what you do, I take power translation. So it goes from the TPM to TQM. Here I have a tensor defined at P, so I just look at the image. It defines for me a tensor at Q. Right? Of course, in general, that doesn't define anything because it depends on the choice of the path. It's not well defined. Well, I claim if my tensor is invariant under the holonomic group at the point, it is well defined because if I take a second path here, so now I have power translation along gamma 1, along gamma 2. I get two different values at Q. I claim they're the same because I can look at the closed path where I take first along gamma 1, then I go gamma 2 inverse. Right? That's a closed path at the point P. The tensor at the point P is invariant under that. That means that if I go this way or this way, I get the same thing at the point Q. And it's well defined. Okay. And also it says that, well, this map from here to here is given by a parallel translation, so this tensor must be invariant under a parallel translation, by definition. Okay, so that's one of the applications of the holonomic group. It helps to define, if you understand the representation on the tangent space and the induced representations on the tensor algebra, if you want to, then you can say a lot about objects on the manifold. So it's very important to understand this. To understand the action on the tensor algebra is a representation theory problem. An interesting one, actually. So, well, maybe I shouldn't say too much about that. Or maybe a little bit. So, for example, an application. If the representation phi p on TPM is a complex representation, so what does that mean? That this is a complex structure. So we have a JP from TPM to TPM. This corresponds identity. And of course, the action is so P gamma applied to JV is complex linear in this sense. This implies that there exists a complex structure on M such that number J is 0. Or in other words, parallel translation is complex linear. Right, so you have a complex structure at the point, you push it around with left with the parallel translation on any path to another point, you get another complex structure there. Right? It's independent of the choice of path because of this property. And then by definition, it's also parallel. Okay. And parallel claim is actually equivalent to saying that parallel translation is complex linear. Another interesting consequence is that
it's almost complex or complex?
It's integrable. So if I have a complex structure, J, with number J is equal to 0, this implies integrable. So it's a general fact about complex structures. Parallel ones are integrable. Does everyone know what an integral complex structure is? So you can find local coordinates where this is multiplication by I. The coordinate interchanges are holomorphic. So it's like a holomorphic manifold. And not every.
The complex structure is compatible with the metric?
Yes.
So you have a K element.
Complex linear and an isometry. Does that mean you have a Kähler manifold? Yes. So what do I need for a Kähler manifold? I want to define a form, a two form. I do it by defining it as Jx square y. That's how I would have to define it if it's part of the definition of being Kähler. Just a side remark if you know what's Kähler. If not, forget about it. Right? So that's a two form. Of course, J is an isometry. Right? That's what we said right here. It's a complex structure, and that implies it's antisymmetric, so this becomes a two form. And when nabla J is equal to 0, well, nabla of the metric is 0, right? If your connection is compatible with the metric, this implies that nabla omega is equal to 0. And if nabla omega is equal to 0, this implies that d omega is equal to 0. Taking more than that also implies that delta omega is equal to 0. It's harmonic. So that makes it into a Kähler manifold. Right? So it's true. So parallel complex structure that's compatible with the metric is a Kähler manifold. So you can see Kähler manifolds in the simple properties of the representation. Right, it's a complex linear. And similar with other things.
I don't know, but this also reduces the holonomy group to a subgroup of SUN too, right?
That's correct. So if it's a complex linear in this sense, right, so that means that this is an element of first of the orthogonal group intersected with the complex linear things. And that was a unitary group. So for such a thing, for a Kähler manifold, the holonomy group is a subgroup of UN.
And parallel transport preserves the orientation, so it's
Because it's complex linear. Any linear map that's complex linear preserves the orientation. No. Anything in UN always preserves the orientation. That's not an additional property. Particularly such a manifold must be orientable. Right? If you have a map that's complex linear, then you have a basis, say, V1 up to Vn, JV1, JVn, that defines an orientation. So to lie in SUN, that's much more special. That's a strong additional condition. So since you asked that, let me mention this. So if the holonomy group, so hol P in UN is if and only if it's Kähler. Hol P in SUN is, of course, Kähler again, plus Ritchie curvature equal to 0. And that's if and only if. It's a very strong condition. Not only is it Kähler, it must be Ritchie flat. Those are sometimes called Calabi-Yau manifolds. So Ritchie flat Kähler manifolds are called Calabi-Yau. So again, you can recognize that in the holonomy group, where the determinant of this as a complex linear map is 1. Right? As a real map, of course, it is 1 by definition, if it's connected. Right? But as a complex linear map, that's an additional condition. And there may not or not be, that depends on the Ritchie curvature. We got off track quite a bit. Natural question certainly is, and I want to maybe discuss a little bit later on. So you have these, they're all subgroups of the orthogonal group. The question is, which groups can be the holonomy group of a manifold? Which subgroups of the orthogonal group can be a holonomy group of a manifold? Clearly an important question, because it tells you about Pell structures. All kinds of geometry follow from knowing what this group looks like. So what subgroups are there? There are very few. And they were classified by Marcel Baget in his thesis, his PhD thesis. And that classification I can discuss later on, because it's very closely connected with symmetric spaces. Okay. And interesting examples are like UN, there's SUN, Kähler, Calabi-Yau, also SPN, that's called hyperkähler. So there are several different lists of interesting subgroups which can be holonomy groups, which imply a very special specific structure on your manifold. So that is a big topic in its own right. Okay. But I want to apply this to symmetric spaces. Right? So what can I say about symmetric spaces? So let M is symmetric. Write it as G mod K, where G is the isometry group. Like we saw, it's homogeneous. So I can write as a homogeneous space under the isometry group. Right? And then the proposition says that in this case, the holonomy group at the point P is a subgroup of K. And of course, the constant, I guess, hol P0 is a subgroup of K0. of the identity component. It says the Horner group is small. That's the way I want to look at this. That's why it's also important. The Horner group is quite small, depending on how small k is. So as an example, we saw that Grassmannian is a symmetric space. We saw that this is SON divided by S of ON O n minus k as a homogeneous space. You might say this implies the Horner group lies in here. Not quite yet, because there's something missing. This here is only true if G is a full isomorphic group and K is a full isotropy. So additional information I'd have to prove here. Do I really know that this is a full isomorphic group of the Grassmannian? That's not clear. So I have to show that SON, or maybe ON, is equal to this identical component of the isomorphic group of the Grassmannian. Once I know that, then I know that the Horner group lies in there. Okay. So it preserves, what does that say? It preserves an orthogonal decomposition, if you want to, into ON and ON minus K. OK, ON minus K, sorry. So these kind of questions here, we're going to discuss later on. It's not so hard to actually decide that. It's true for almost every symmetric space. Okay. In fact, we're also going to see later on that it's essentially always true that these two groups are the same. It never happens that they are different. The only example is essentially Rn. That's, of course, a symmetric space. And what's the isomorphic group of Rn? Well, you have rotations, and you also have translations. So, it's a semi-direct product, so this way maybe you forget which way it goes. But you have translations, and then you have also have rotational compositions of those, right? That's the full isomorphic group. So if I write this as a quotient isomorphic group, Rn becomes On cross translations divided by the stabilizer, say, or the origin, and that's, of course, only the rotations, like On. The group K here is On. Okay. But what's the holonomy group? What's the Horner group of Rn with the usual metric? So I take parallel translation on a closed path in Rn, I get identity. The group is trivial. So it's as big a difference as you want, right? So it's not always a quality, but apart from these counterexamples, it is. It's not in a certain sense I'm going to specify later on. So I can compute the Horner group as a symmetric space, and it's small. That's kind of surprising. So how do you prove this? Actually not hard now. First, of course, notice that in what sense does this make sense here? K, X, and TPM. Why what we call the isotropic representation? Right, you take an element K into the action of K on the manifold, if you want to. Derivative of that at the base point P. And of course, whole P sits naturally also inside, acts on the tangent space, sits inside the orthogonal group. And so does K. It also sits inside, it acts by isometries. So they both sit inside the orthogonal group. So the equality is meant in that sense, as a subgroup of the orthogonal group. One's contained in the other. Another thing that I mentioned earlier on was that K is compact. So G was an isometry group, that's not necessarily compact, but the stabilizer, the isotropy group of all isometries is compact. I'll actually be able to give a proof of that next time. It's kind of interesting to understand why K is compact. So those are the properties I want to use. So now let's try to see why whole P sits inside K. So what do we have to prove? So take a closed path, starting at P, have pair translation from Tpn to itself. I want to show that this lies in K. What is K? So I have to know there's some isometry of the whole manifold which fixes the base point. Right now we just have an isometry from P which comes from a single path. It's not defined at other points. Right? So that's kind of surprising, in fact, that I can kind of extend this isometry to the whole manifold. Right? So how do I do that? I do it as follows. So I claim there exists a sequence gamma I converging towards gamma, where gamma I are piecewise geodesics. In other words, I can approximate every closed path by piecewise geodesics. How do I do that? Well, I subdivide into many small pieces and then connect by the unique geodesic that connects the 2 points. Right? So I know for a manifold, around each point there's a normal ball. In a normal ball, I can connect any 2 points by a unique minimal geodesic. The curve gamma is compact. I can cover it with finite dimensional normal balls. And now I can connect just base points like this. And then, of course, I can make the subdivision finer and finer. Right? First choose 100 points, then 1,000 points, and so on. Make it finer and finer. I get always a piecewise geodesic. But then as I goes to infinity, in the limit, I get the closed curve gamma. Okay. Now, pair translation is given by a differential equation. So I claim that implies that P gamma I converges towards P gamma also. Right? Pair translation is just nabla is equal to 0. I have to know the metric. I have to know the connection. But if I have a path, points converging to a point, and paths converging to a path, the connection converges to the connections continues after all. Right? So parallel vector fields go toward parallel vector fields. And what can I say about P gamma I? P gamma I claim is a composition of transvections. So draw the picture here. So here I draw a piece of that. Right here's a piece. If I want to pair translate from this point to this point, well, this here is a gamma geodesic gamma. I just choose a transvection along this geodesic which takes this point to this point. But this is the thing we've proved earlier, that for any geodesic, I have this one parameter group of isometries, globally defined isometries, which along the geodesic give me pair translation. So from here to here, I have one transvection. That's a global isometry. From here to here, I have another transvection. That's a global isometry. Compositions are global isometries. So that means that P gamma I is an element of K. Right there. K is the isometry that fixes the point. P gamma I's are a composition of many isometries. And I always come back to the point P, so the fixed point P. So it lies in K. And now by compactness, since K is compact, P gamma also lies in K. Because it's the limit of things that lie in K. So now I have to use compactness. That's very important.
Can you say again why the pattern transport operators shouldn't converge?
Why this converges here?
Yes.
So what's the differential equation? So I have a curve gamma, and its nabla c dot x is equal to 0. Right. I could write this down in local coordinates. Then it would be something like c double prime I plus Christoffel symbols. How does that go? That's the differential equation for a parallel vector field. Sorry. Xi. I wrote down the equation for a geodesic. What does it mean for a vector field to be parallel? It's probably something like this. I think that's what it is. Anyway, there's some differential equation where I can write on local coordinates. And it's given by Christoffel symbols. Christoffel symbols are continuous, they're smooth. Right? So if I have a curve gamma, I converging towards another curve gamma here, I guess I have to know also that
SC1 convergence.
that the tangent vectors converge should be C1. At almost every point, at least, should be C1, right? And then the differential equations converge towards other, and then the theorem on continuous dependence of the differential equation of parameters implies the solutions must also converge with each other. So here, so of course, you write to be specific, I have to say that gamma I converges towards gamma in C1 almost everywhere. And that's what I do with this kind of connection. Okay. So make it smaller and smaller, it converges towards this, in this C1 sense. Okay. And then I can use these transvections along each piece. So transvections are really neat. That lies in K. Okay. Applications of that is some decomposition. And for this, I have to review another important property of the holonomic group. In fact, probably the most basic one, maybe the original application, namely, I want to see when can I decompose a manifold into products. So let's say I have a manifold M. M is called reducible. If M is equal to M1 cross M2 with a product metric. So not only is the manifold is a product, but also the metric is a product. And I see the manifold is reducible. And clearly you would like to study manifolds, but you can't decompose like this because usually products are easy to understand. So I say if not, M is called irreducible. So one usually wants to understand irreducible manifolds. So how can I tell whether something's irreducible or not? Well, that claims a holonomic group. So here is what's called the Durand decomposition theorem. So I have a manifold M. I fix a point P. I have a holonomic group at the point P. And I assume that M is simply connected. Which means that hol P is hol P0. It's a connected group. And compact. It's connected and compact. So it acts in tangent space. So if I have a compact group acting in a tangent space, I can now decompose into irreducibles. So in other words, write TPM as a V1 plus VK such that all P, let's start with 0. All P acts irreducibly on VI. What does it mean for representation of irreducible? Right, there's no subspace which is invariant under the whole group. Right, so no invariant subspaces. For I bigger than 1, and the first one, V0, is defined as those vectors in TPM where HV is equal to V for all H in the holonomy group. So first look at vectors that are fixed. There might be none. If they are collected into a single subspace, that's a linear subspace. On X the holonomy it's trivially. On the rest it acts non-trivially and irreducibly, so no invariant subspaces. First one has to make a remark, why can I do that? So we haven't talked about representation theory, but that's an easy... Pardon? Right, so what's the argument? Well, you could do it by hand.
Every representation of a semi-simple group is...
Do it by hand, come on. It's a two-line proof. So Hall P is compact. It acts by symmetries. So what if I have an invariant subspace? So take some invariant subspace. Then the Thorne complement is another invariant subspace because K acts by symmetries. So for each subspace I have another complement that's also invariant, and now I can keep on going. If this one's not irreducible, I have another subspace. Take its Thorne complement. That process is finite, so you must end up eventually with a sum of irreducible subspaces. Plus one, of course, on which it acts trivially, possibly. That I separate from the beginning. So that's very easy.
So
compact.
what matters is that it is a group isomorphism.
Pardon?
What matters is that it is a group isomorphism.
Correct.
With the proper capacity.
Correct. So it's also true for semi-simple complex representations. It's also true. One way to visualize that or to prove it is to show that every semi-simple Lie has a compact real form. It's a complexification of something compact. In the compact case, I just do this argument, then complexify. So algebraically, there are different proofs algebraically. If you don't talk about Lie group ever, only about Lie algebra, so you have to prove this algebraically. Then you have to work. That's true for every semi-simple complex Lie algebra. But if you think about geometrically, let's take a compact real form, then it's obvious. Okay. So that's the way I do it in the notes when I do representation theory. Let me add, oh yeah. That's my setup. So I take my tangent space, split the actional holonomy group into irreducibles. And what's the conclusion? The conclusion is then is that M is equal to M1 cross M0 cross M1 cross MK in the sense of a product metric. So metric splits as a product metric, and M0 is flat. This coverage is 0. And the tangent space, so what's point P? So tangent space of Pi at Mi is Vi, where P is equal to P0 up to Pk. Right, so I'm doing this as a base point. I fix the base point and split it into it. A base point in a product manifold is just a bunch of points in each vector. So then at the point Pi in the ith vector, I can look at its tangent space. And of course, I can think of this naturally sitting inside the tangent space of a product manifold. It's a natural subspace. And it's equal to that Vi. Okay. So once I split the tangent space at one point, introduce a harmony, the whole manifold splits everywhere. And furthermore, decomposition is unique up to order. And all P is all P1 cross all Pk, but all P0 is trivial. So the harmonic group just splits up also into products. And what's also important, the asymmetry group splits up into products. So every asymmetry, just an asymmetry on each factor. That looks obvious, but it's not obvious at all. Right? An asymmetry, why should you preserve the factors? I claim it follows from uniqueness up to order. And so take my decomposition. I can only change the order of the factors. I can't change anything else. Choose an asymmetry of M that induces a new decomposition. It says that all I can do is change factors. Otherwise, it preserves it. But changing factors is not allowed because I'm taking the identity component. Changing factors, I can never homotop to something that doesn't change factors, that generates another component. So, for example, for S21 cross S21, what's the asymmetry group? Well, it's O3 for H2 sphere plus the switching. That generates another component. Right? It's not of this form. So this actually has 4 components, the asymmetry group of this here. So here it's saying at least the identity component must split, which in this case would be SO3 cross SO3. There could be other asymmetries which also split, but they may not, because it could look like this. That's what it says. So this here is a very useful property, that the asymmetries preserve factors. That's called the Durand decomposition theorem. It's a beautiful theorem. Let me just indicate maybe one idea that makes it believable. Proof is involved. I think it's in Kobayashi and Mitsu, for example. So what's the first thing one should think about that's maybe surprising is I have just a splitting at one point Vi, right? I have to find somehow locally, at least locally, submanifolds. How do I find the mi's locally? The rest would be something global that involves that is simply connected. I need this. So how do I do this locally? I think it's quite natural. What I do is the following. In fact, it's similar to what I said before. Say in a neighborhood of P, I can do the following. Define the distribution. Say, let's call it Vi tilde. By pair translation of Vi. So why is that well defined? Because whole P preserves this. Right? So along any path, doesn't matter which path I choose, I pair translate this vector space V at this point. But if I choose a different path, it's independent because along the closed path, it preserves the Vi. My holonomial principle. So at least I can now get a well-defined distribution, and this distribution, by definition, is parallel. So locally, just from the definition, you immediately get a parallel distribution, a bunch of parallel distributions. Of course, now I'd like to show it's integrable. Right? That's supposed to be MIs, at least locally. Why is it integrable?
It's evolutive.
Why is it involutive?
Because of the power.
Why is that?
When you
So what he's saying that every parallel distribution is involutive. That's a completely general statement.
But you're restricting the directions in which you want to derive.
So why is a Lie bracket lie in it, right? So we have to prove that x and y are vector fields in vi tilde. I have to show Lie bracket lies in it. That's what involutive means. So why is that?
But you lose the symmetry of the connection.
So what is this here? It's nabla xy minus nabla yx. Conjugative you can define in terms of parallel translation. If parallel translation preserves the distribution vi, this again lies in vi. So does this one, therefore the difference. Therefore this is tangent again, that means integrable. So I have local leaves at least for these MIs. That makes it believable, right? Because now I have work to do. I have to show the metric is a product, that actually even the neighborhood is really a product, that the metric is a product. That requires some work, it's not that obvious. Then I have to make it global, assuming the manifold is simply connected. So the whole proof is work. But the idea behind it that makes believable is just this kind of principle, that it naturally, by the holonomic principle, defines a parallel distribution. Those are always integrable. Those are going to bring up my MIs locally. Okay, so next I want to apply that to symmetric spaces. So today was just a bunch of backgrounds on holonomic groups and applications. Okay, now I'm going to pass out the take-home exam.